Hi, hello, namaste. Welcome to today's talk on Ampere's circuit law. I am Dr. Kasigari Prasad, Associate Professor, Graphologist, Writer and Motivational Speaker from Annamacharya Institute of Technology and Sciences, Rajampet. In our previous lecture, we have discussed on Biot-Savart's law. In continuation to that, today we are supposed to discuss on Ampere's circuits law, which these two laws, Biot-Savart's law and Ampere's circuits law, are very important and plays vital role in analyzing magnetostatic fields. So, before we go to the talk, I request respected faculty members, students and all the learners kindly take a notebook and pen to write the important points and equations for better understanding of this particular electromagnetic theory subject. Now, Ampere's circuit law. Very first we define what is the statement of Ampere's circuit law. Ampere's circuit law states that the line integral of the tangential component of H around a closed path is the same as the net current I enclosed by the path. To analyze this one, let us discuss that in a different way. The circulation of H equals I enclosed. That means in a conductor, when current I is flowing or moving, around that conductor some magnetic field is supposed to produce. That circulation of magnetic field around that conductor is equal to the amount of current that is enclosed in that particular conductor. This is the simple understanding. For that, closed integral H dot dl is equal to I enclosed is the first equation. So, closed integral H dot dl is equal to I enclosed. This is Ampere's circuits law. And what is the observations from these equations? Ampere's law is similar to Gauss law. Ampere's law is easily applied to determine H when the current distribution is symmetrical, and this equation 1 always holds good whether the current distribution is symmetrical or not, but we can only use this equation to determine H when symmetrical current distribution exists. As similar to Gauss law, when Gaussian surface is existed, then only we can apply Gauss law. Similarly, Ampere circuits law can also be applicable when and only if Amperian circuit is available. Amperian circuit or Amperian path is nothing but a symmetrical current distribution is to be prevailed. So, Ampere's law is a special case of Biot-Savart's law. These were the observations. Now, we know that closed integral H dot dl is equal to I enclosed. This is the statement of Ampere's circuits law. Now, applying Stokes theorem to the left hand side of this first equation, that means the above equation, we can obtain. Generally, we know the relation Stokes theorem, closed integral L A dot dl is equal to integral S del cross A dot ds. This is the definition of Stokes theorem. Now, with respect to this, we apply it for our first equation. What is our first equation? I enclosed is equal to closed integral H dot dl. And now that is equal to, that means closed integral L H dot dl is equal to integral S del cross H dot ds as per the Stokes theorem. Now, but we also know that I enclosed, current enclosed, he is equal to the amount of current density circulating there. Therefore, that is integral S J dot ds is the next equation. Therefore, integral S J dot ds is equal to the above equation, closed integral L H dot dl, that is equal to integral S del cross H dot ds. Now, from this equation, if we equate the surface integrals, then we get integral S J dot ds is equal to integral S del cross H dot ds. So, we get a clear understanding of equating two surface integrals stating that integral s j dot ds is equal to integral s del cross h dot ds. Now if you remove that integrals, we will go for a conclusion that del cross H is equal to J. This is a Maxwell's equation number 3, or the third Maxwell's equation. Del cross H is equal to J. This is Maxwell's equation in the integral form. Closed integral H dot dl is equal to I enclosed is the Maxwell's equation in differential form. So what is we observed here? It is observed that del cross H is equal to J, and it is not equal to 0 here. So magnetostatic field is not conservative. Magnetostatic field is not conservative. That is the conclusion. Now to analyze this Ampere circuit's law, let us go for application of this Ampere's law. Ampere's law application. So we can apply this Ampere's law as similar we have performed for Gauss law in electrostatic fields. Now let us see. With the help of Ampere circuit's law, we can easily determine H, magnetic field, for some symmetrical current distributions, and the definition for Ampere's law is closed integral L H dot dl is equal to I enclosed. So for a symmetrical current distribution, H is either parallel or perpendicular to dl. When H is parallel to dl, magnitude H is constant. Now we can apply this Ampere circuit's law for 3 applications, like infinite line current, an infinite sheet current, and infinitely long coaxial transmission line. For these 3 categories, we are going to apply Ampere circuit's law. Let us see the first one, infinite line current. Let us consider an infinitely long filamentary current I along the z axis as shown in the figure. So in the figure we have x axis, y axis, z axis, and a filamentary current carrying conductor is placed here, which is infinite, and the current moving here, it is I as shown in the z direction, and we have drawn an Amperian path. That means the magnetic field is produced across that particular conductor, circulating around that conductor. So we have drawn an imaginary path. That path is a closed path indicating Amperian path. It means that it is having symmetry nature there. So at a particular point on that Amperian path, that is point P, we are going to find out the magnetic field produced capital H. Therefore we have taken a differential length dl here, and also the distance from origin O to point P is rho. This is shown in the diagram. With reference to this diagram, let us see. To determine H at observation point P, draw a closed path that passes through point P. On this path, Amperian law is applied. So this path is also known as Amperian path. This is as similar to our Gauss law. Now from the concepts of Biot-Savart's law states that for a conductor of infinite length, we have already defined in our previous lecture. For a conductor, as per Biot-Savart's law, that to infinite conductor, the magnetic field produced is equal to H is equal to 1 over 2 pi rho into A phi. This is we have done in our previous video. If you want, you please refer our Biot-Savart's law video lecture. Now, according to Ampere's law, the total current enclosed I is equal to integral H dot dl is the equation. So that we have written as I is equal to integral H phi A phi dot dl. The differential length is rho d phi A phi. Distance is rho d phi A phi. Therefore, you have taken H phi outside, integral rho d phi. Rho d phi, the distance is nothing but a circle. 2 pi rho is the distance covered, that means area. So H phi dot 2 pi rho. So H is equal to I divided by 2 pi rho into A phi. This we have defined as per the Ampere circuit's law. The amount of magnetic field produced for an infinite line current. Now let us see for an infinite sheet of current. Here let us take, we have taken a sheet and placed horizontally in the coordinate system x, y, z. Here the concept is consider an infinite current sheet in the z is equal to 0 plane. If the sheet has a uniform current density, the current density is uniform, and that is K is equal to Ky Ay amperes per meter. as shown in the following figure, ky ay. See, we have applied these currents are moving along y direction as shown in the figure in the direction arrow marks. There we have taken k is equal to ky moving in ay direction, ay. So here we have taken an Amperian path from 1 to 2, 2 to 3, 3 to 4 and 4 to 1. The horizontal distance in that Amperian path is b from 2 to 3 and 4 to 1 also. Similarly, the vertical distance from 1 to 2 is a, and from 3 to 4 is also a, vertical distance. It means that the current is moving from top to bottom, from bottom left to bottom right, and bottom right to top right, and from top right to top left, creating a closed path. That is 1, 2, 3, 4 and 4 to 1. This is the direction of your current flowing. Now applying Ampere's law to this rectangular closed path 1, 2, 3, 4, 1. What is Ampere's law? Closed integral h dot dl is equal to I enclosed, and that current enclosed is due to the current density ky that is moving in y direction. Means what is the length of that y? B. See, as in the b, b is the length, horizontal distance to say b. That is our first equation. In order to evaluate the integral, we first need to know about h. To study about h, let us consider that infinite sheet consists many of the filaments dh above and below the sheet. That means on the top of the sheet as well as at the bottom of the sheet, we find so many similar types of infinite sheet filaments. So let us find it for one filament and then integrate it. These pair of filamentary currents will produce some h, and it can be found using equations as given below. So h is equal to I divided by 2 pi rho into Fi. H is equal to I divided by 2 pi rho into Fi, which we have defined in our previous topic. And Fi is equal to Al into A rho. Fi is equal to Al into A rho. Now we can understand that H on one side of the sheet is negative and on the other side it is positive. The magnetic field produced on the one side it is negative, on the other side it is positive. Since the sheet is infinite, the sheet can be assumed as it is consisting of such filamentary pairs. ఒక నోట్బుక్ని మనం రెఫరెన్స్గా తీసుకుంటే నోట్బుక్కి మనము హారిజాంటల్గా ప్లేస్ చేసినప్పుడు టాప్ సైడ్ మనం ఎంతైనా కొంత ఏరియాని తీసుకొని దీని ఫిలమెంటరీ సర్ఫేస్ అని అనుకుంటే ఇదే ఏరియా బాటమ్ సైడ్ కూడా ఉంటుంది. సో టాప్ అండ్ బాటమ్ సేమ్ ఉంటాయి. సో అలాంటివి ఆ నోట్బుక్ సర్ఫేస్ పైన అంతా చాలా ఉంటాయి. అలాంటి నోట్బుక్ సర్ఫేసెస్ పైన, అలాంటి ఒక షీట్ పైన కే అనే కరెంట్ డెన్సిటీ ఉంటే ఆ కరెంట్ డెన్సిటీ వల్ల ప్రొడ్యూస్ అయినటువంటి మ్యాగ్నెటిక్ ఫీల్డ్ హెచ్ని మనం అట్ ఏ పాయింట్ పి దగ్గర క్యాలిక్యులేట్ చేస్తున్నాం. సో దానికి రెఫరెన్స్గా సిన్స్ ద షీట్ ఈజ్ ఇన్ఫైనైట్, the sheet can be assumed as it consists of such filamentary pairs. So the characteristics of H for a pair are the same as that of infinite current sheet. So infinite current sheet ki evaithe untayo that is supposed to come here. So H is equal to the total magnetic field H is equal to, ఇప్పుడు టూ కేసెస్లో తీసుకుంటాం. అట్ z is equal to 0 దగ్గర మనము సర్ఫేస్ని ప్లేస్ చేసినాం, దట్ మీన్స్ అవర్ షీట్ని ప్లేస్ చేసినాం. So over z is equal to 0 and below z is equal to 0, that is z greater than 0 top side వస్తుంది, z less than 0 it comes under bottom side. At these two particular cases లో మనం మ్యాగ్నెటిక్ ఫీల్డ్ని మెషర్ చేయబోతున్నాం. z greater than 0 అంటే ఇప్పుడు వర్టికల్ డిస్టెన్స్ని కన్సిడర్ చేయాల్సి ఉంటుంది. సో h is equal to, let us consider that it is having a magnetic field produced is h naught. So h is equal to h naught in ax direction for z greater than 0. Similarly in the bottom side it produces h naught magnetic field, but it moves in the negative direction, therefore it is minus ax direction. This is the thing we have assumed from that filamentary sheet. Now let us determine that the value of that h naught also. So evaluating the line integral of h in equation 2, we are going to evaluate the line integral of h along the closed path as shown in that particular figure. సో 1 నుంచి 2కి, 2 నుంచి 3కి, 3 నుంచి 4కి, 4 నుంచి 1కు ఈ క్లోజ్డ్ పాత్లో ఈచ్ పాత్ దగ్గర ఎంత మ్యాగ్నెటిక్ ఫీల్డ్ ప్రొడ్యూస్ అయిందని మనం ఇప్పుడు ఎవాల్యుయేట్ చేయబోతున్నాం. దాన్ని టోటల్ చేస్తే ద టోటల్ అమౌంట్ ఆఫ్ మ్యాగ్నెటిక్ ఫీల్డ్ ప్రొడ్యూస్డ్ ఫ్రమ్ దట్ పర్టికులర్ యాంపీరియన్ పాత్ అని మనం తీసుకుంటాం. సో క్లోజ్డ్ ఇంటిగ్రల్ హెచ్ డాట్ డిఎల్ ఈజ్ ఈక్వల్ టు ఇంటిగ్రల్ 1 to 2 ప్లస్ 2 to 3 ప్లస్ 3 to 4 ప్లస్ 4 to 1. We are all evaluating magnetic field కదా. సో హెచ్ డాట్ డిఎల్. సో 1 నుంచి 2 వరకు ఉన్నటువంటి మ్యాగ్నెటిక్ ఫీల్డ్ ఇట్ ఈస్ మూవింగ్ ఇన్ ద నెగిటివ్ డైరెక్షన్. నెగిటివ్ సైడ్ డైరెక్షన్లో ఉన్నటువంటి మ్యాగ్నెటిక్ ఫీల్డ్ హెచ్ నాట్ని మనం 0 అనుకుంటున్నాం. సో 0 అండ్ ఇట్ ఈస్ మూవింగ్ ఇన్ నెగిటివ్ డైరెక్షన్, కిందికి బాటమ్ సైడ్ మూవ్ అవుతుంది కాబట్టి -a ప్లస్ 2 to 3 ఇట్ ఈస్ మూవింగ్ అలాంగ్ ద లెంత్ b కాబట్టి దట్ ఇన్ ద నెగిటివ్ సైడ్ మూవ్ అవుతుంది కాబట్టి వీ హ్యావ్ టేకన్ హెచ్ నాట్ మైనస్ హెచ్ నాట్ ఇన్ ద బాటమ్ సైడ్ ఉంది కాబట్టి -h నాట్ మైనస్ b డిస్టెన్స్ ప్లస్ 3 to 4కి హెచ్ నాట్ 0 అంటే బాటమ్ సైడే ఉంది కాబట్టి దాని వర్టికల్ డిస్టెన్స్ లెంత్ ఎంత ఉంది, a ఉంది కాబట్టి 0a ప్లస్ 4 to 1కి ఎంత ఉంది, మ్యాగ్నెటిక్ ఫీల్డ్ హెచ్ నాట్ అంటే అప్పర్ సైడ్ డైరెక్షన్లో ఉంది కాబట్టి అండ్ లెంత్ ఈస్ b. సో హెచ్ నాట్ b. సో ఫ్రమ్ దిస్ వీ కెన్ టోటల్లీ సమరైజ్ ఇట్ యాజ్ 2h నాట్ b. అంటే ఒక నోట్బుక్కి మనం ఇప్పుడు రెఫరెన్స్గా తీసుకున్నప్పుడు టాప్ సైడ్ ఉన్న దగ్గర మటుకే కన్సిడర్ చేస్తున్నాము, బాటమ్ సైడ్ ఉన్నటివి ఇట్ ఈస్ గోయింగ్ టు కన్సిడర్ టు బి నెగిటివ్ వాల్యూస్. ఓకే, దాని రెఫరెన్స్గా మనం ఈక్వేషన్ రాసుకున్నాం. వీ హ్యావ్ రిటర్న్ దిస్ ఈక్వేషన్. సో ఫ్రమ్ ఈక్వేషన్ 1 అండ్ ఈక్వేషన్ 3, ఈక్వేషన్ 1 and equation 3, this is equation 3, we might have identified that h naught is equal to 1/2 of ky. Now substituting this fourth equation in second equation, we write h is equal to integral 1/2 ky into ax for z greater than 0 minus 1/2 ky into ax for z less than 0. ఈ కంక్లూషన్ మనం తీసుకుంటున్నాం. ఫర్ అన్ ఇన్ఫైనైట్ షీట్ ఆఫ్ కరెంట్ డెన్సిటీ k amperes per meter, generally the h is given as h is equal to 1/2 k. ఆ ax అనే డిస్టెన్స్ని మనం నార్మల్ డైరెక్షన్లోకి తీసుకుంటున్నాం అంటే an 1/2 cross an, where an is unit normal vector directed from the current sheet to the point of interest. This is how we can calculate the amount of magnetic field produced from infinite sheet. Now we continue for infinite long coaxial transmission line. Let us consider an infinite long transmission line consisting of two concentric cylinders having their axis along z axis. As shown in this particular figure, మనకు ఒక 2 coaxial transmission lines ఉంటాయి which has inner conductor as well as outer conductor and 2 concentric cylinders ఉంటాయి. Okay, the inner conductor has radius small a and carries I, current I, while the outer conductor is having radius b and thickness is t and it is carrying current -I. So inner conductor యొక్క radius small a, outer conductor యొక్క radius small b, inner conductor is carrying current I and outer conductor is carrying current -I. Now we want to determine h everywhere, assuming that current is uniformly distributed in both the conductors and also the current distribution is symmetrical. Since the current distribution is symmetrical, we can apply Ampere circuit's law. So while applying Ampere circuit's law, here we will have 4 different possible regions. So ఏంటివంటే ఇన్నర్ కండక్టర్ లోపల మనం గానే కన్సిడర్ చేసి మ్యాగ్నెటిక్ ఫీల్డ్ని క్యాలిక్యులేట్ చేస్తే ఇన్సైడ్ ది ఇన్నర్ కండక్టర్, దట్ మీన్స్ లెస్ దాన్ రేడియస్ a. Okay, next one we are going to consider ఆ ఇన్నర్ కండక్టర్ కన్నా ఎక్కువ outer కండక్టర్ కన్నా తక్కువ, దట్ మీన్స్ above ఇన్నర్ కండక్టర్ రేడియస్ and less than outer conductor radius. So less than outer conductor radius, so it is ranging between a and b. Next one, that outer conductor is having a thickness small t, so we are taking a radius on that outer conductor thickness, therefore the radius is ranging between b and b plus t. And the last case is we will take a radius which is greater than, we will take a distance or radius which is greater than the outer conductor, that means b plus t. Likewise 4 different categories we will be having, each category we have to discuss. So for the first region, for radius 0 less than or equal to rho. Rho is the distance at which we are going to find the magnetic field. Rho less than or equal to A, first category. So for each category we will plot their respective Amperian paths. See, as shown in this figure, we are having L1 Amperian path less than radius A, L2 Amperian path greater than radius A and less than radius B, and Amperian path 3 in radius rho B plus T, and the last one is Amperian path L4 above B plus T, as shown in this diagram. Okay. Now with reference to this, for the first case we are going to apply Ampere circuit's law. As we know, Ampere circuit's law defines that closed integral L1 H dot dl is equal to I enclosed, that is equal to integral J dot ds. I enclosed is equal to J dot ds. Since the current is uniformly distributed over the cross section, we can write this current density J is equal to current per area, that is I divided by pi a square in az direction. Okay. Therefore ds is equal to, we are now finding the differential surface area, ds is equal to rho d phi d rho in az direction. Okay, in az direction. With reference to this, I enclosed is equal to integral J dot ds, that is equal to integral I whole divided by pi a square az, and the ds rho d phi d rho az. Now we take constant outside, I divided by 4 pi a square, phi is equal to 0 to 2 pi, rho is equal to 0 to a, rho d phi d rho. Now we integrate this one and go for a simple calculation. We got here I enclosed is equal to closed integral J dot ds is equal to I rho square divided by a square. Here limits of rho is not substituted in order to obtain a generalized form. That is the clarification. Okay. Next, for the second region, A less than or equal to rho less than or equal to B, second region radius. Here the Amperian path is L2. So closed integral L2 H dot dl is equal to I enclosed, that is equal to integral J dot ds. So closed integral L2 H dot dl is equal to I enclosed, that is equal to I. See, what is the amount of current that is moving in the second Amperian path, that is I. So H phi, and that second path area is 2 pi rho. So H phi 2 pi rho is equal to I. So H phi is equal to I divided by 2 pi rho. This is for the second region. Now apply Amperian path for third region, that is B less than or equal to rho less than or equal to B plus 3. Now the Amperian path is L3. Now closed integral L3 H dot dl is equal to I enclosed is equal to I. H phi 2 pi rho is equal to I enclosed. So I enclosed is equal to I plus integral J dot ds. J in this case is the current density of the outer conductor and is along minus az direction, and is along minus az direction. Therefore we have to find J value. So J is equal to minus I divided by area, pi r square, no, that is B plus T whole square minus B square into az. So I enclosed is equal to I minus I divided by all the value, all the above term, and we have to integrate it for phi is equal to 0 to 2 pi, rho is equal to B to rho, rho d phi, rho d rho d phi, and that value is equal to I enclosed is equal to I into 1 minus rho square minus B square divided by T square plus 2bt. Substituting this value in the above equation, we get closed integral L3 H dot dl is equal to H phi 2 pi rho, that is I enclosed. We get H phi is equal to I divided by 2 pi rho of 1 minus rho square minus B square divided by T square plus 2bt. In this way, for 4 different categories we can find the magnetic field produced, and the last region is rho greater than B plus T and Amperian path is L4. So closed integral L4 H dot dl is equal to I enclosed, that is equal to the current, total current moving is I, and the current that is moving in the outside, that one is minus I. So I minus I, that is equal to 0. So we can summarize the total H at 4 different categories as H is equal to I rho square divided by A square into A phi for 0 less than or equal to rho less than or equal to A. I divided by 2 pi rho into A phi for A less than or equal to rho less than or equal to B. I divided by 2 pi rho into 1 minus rho square minus B square divided by T square plus 2BT into A phi for region B less than or equal to rho less than or equal to B plus T, and at the last case it is 0 for rho greater than or equal to B plus T. This is the conclusion of Ampere circuits law applications. So likewise we can determine the amount of magnetic field produced for different categories of conductors, that means sheet, line surface, sheet and coaxial cable. Thank you all for watching and listening and understanding the subject electromagnetic waves and transmission lines. This is Dr. Kasigari Prasad, Associate Professor, Graphologist, Writer and Motivational Speaker. So in this way I would like to encourage and inspire the students in learning subject, and also I am inspiring students through motivational talks through YouTube, and therefore I request all of you to kindly subscribe Kasigari Prasad YouTube channel and share this valuable information to many of your friends, colleagues and to your family members. Thank you. Jai Hind, Jai Bharat.